background so I can kind of explain the problem space and describe what the goal of the software models at the end are talking about. So the first thing I want to talk about is what are buses and bridges? And so it sounds kind of very basic, but we can think of computers as being that computer systems contain a lot of different components, things like processors or memory or I/O devices. And those things need to be able to communicate with each other. And so we connect all these components inside a computer system using buses. So traditionally, it's like actual wires that we send signals over to allow communications between devices. Nowadays, some buses use wires and some buses are not because it's all contained in one IC. And then, so that's kind of talks about what buses are. Buses are a channel to allow different components to talk to each other. Well, bridges are a kind of special device that are connected to at least two buses, usually kind of two different buses, and they allow messages to flow between different types of buses. So we can pass messages to components that aren't directly connected to each other, but kind of across some kind of hierarchy or path. And so bridges can forward requests, and in some cases that might need to translate or modify the request as it's transiting the bridge. And traditionally in a computer system, these components that we can think of, they're basically organized in some kind of hierarchy, some kind of tree-like structure. So here's a picture, and somewhat abstract, of what a device hierarchy might look like in a computer system. I mean, I know in some cases on modern CPUs, a lot of these things actually get shoved into the package, and so it's not quite as cleanly broken out as this abstraction. But at the top, we have a couple of processors. We have some memory that they're connected to over some kind of system bus that connects CPUs directly to RAM. Then we have some kind of I/O controller that's going to deal with DMA requests from devices and kind of allow access from the CPUs down through the I/O controller out to I/O devices. And those I/O devices are connected via different types of buses. So in most, at least like the x86 systems that we work with, that first level I/O bus is going to be a PCI Express bus. And so then it's got PCI devices as children of that. And some of those devices, you might have PCI bridges that we'll talk about later, but we also have other kinds of bridges. In a way, well, logical bridges that you might think of. Something like a SATA controller or a USB controller that allow you to communicate over a different type of bus on the back end. So a SATA bus is very different than a PCI Express bus, for example. And yet, those controllers do kind of provide a way that a CPU can send a request down to a SATA disk, and it crosses all these things. So then, part of my title was managing resources in bus drivers, and we've talked a bit about what buses are and bridges and kind of special devices those are. So what kind of resources am I talking about? Because there's all sorts of resources that operating systems manage, especially if you've been to any CS undergraduate OS course, you talk about all sorts of resources. And we're not talking about things like CPU time, we're talking about a few very specific things. And two in particular that I'll kind of probably talk about most. The first is devices have registers. That's how you configure devices and control devices directly from the CPUs. You read and write registers, usually using memory mapped I/O of some sort. So being able to control access to those registers, maybe being able to decide where those registers live in your memory address space. That's one of the kind of resources a bus driver will manage. And the second one are interrupts. So I, as a device, want to be able to interrupt the CPU. So I'm connected maybe logically to a pin on the interrupt controller, or PCI has message interrupts, which are another ball of wax. But I have some way of interrupting the CPU, and I need to be able to do that reliably and ensure that I can register an interrupt handler, and my handler gets called when I interrupt the device and not some other handler or no handler or things like that. So let's talk a bit more about memory mapped I/O and kind of what that looks like and a bit of what the kind of the problem that we have to address inside our device driver system. So I have here kind of a diagram, and I'll stack a bit more, of roughly what the physical memory address space looks like in a kind of typical x86 system. So we've got RAM, mostly, from about 0 up to about 3.5 gig. Ignore old legacy ISA things. Then we have a hole up to about 4 gig for memory mapped I/O. That's generally used for kind of low 32-bit PCI things. Then we have a bunch more RAM, and then maybe at the top of that, somewhere, we have some more MMIO, and then we have things that aren't even used. So let's look a little bit more detail about the middle region here. So in this middle memory I/O region, that itself is kind of subdivided and shared across different devices. So you might have a big chunk at the bottom, and that's used for the frame buffer for the GPU. And then you might have some other devices like some kind of NIC and USB, and then we have some things that are architectural to x86 to deal with interrupts and interrupt controllers at the top. And then if we drill down a bit further, inside the NIC, we might have a couple of registers, things like the base address maybe of transmit and receive descriptor rings or an interrupt status register. And so in particular, what happens in hardware is if you're trying to read, say, the interrupt status register in your NIC, is you're doing a load or store on the CPU against, well, eventually a physical address. Just pretend the MMU is not here for the purposes of all that we're talking about. So you're going to do a load or store trying to address the interrupt status register. And what happens at the top level is when you do the load or store, RAM doesn't kind of claim the access. Instead, the top level PCI bridge in this case is going to actually claim the access and say, hey, it lives inside my little window between 3.5 and 4 gig. And then that's going to go onto the bus. And then on the bus, the NIC is going to say, the address you passed, that falls into my range. So I, as the NIC, am going to claim this kind of read request. And then inside the NIC, it'll look at the relative offset and figure out, oh, the register you're actually going is my interrupt status register. I'll read the value, and I'll send the reply back. So we kind of have to filter each level down to figure out who does this address belong to. So now let's talk a little bit about bridges and the role they play in kind of what we just described and how we deal with bridges and memory mapped resources in particular. So bridges can use something called a window. And a window is kind of like, well, it's not kind of like it. In a window, the bridge allocates a chunk of address space, usually memory or I/O ports, from its parent, and then it subdivides that address space to hand out smaller chunks to child devices that are behind the bridge. So this is how a device behind a bridge can get access, is that the bridge allocates a bigger window, and it'll claim anything in that window, and then it'll forward the request on to the children beneath it, and then give the children beneath it a chance to claim the request as it passes through. But if a child tries to listen for a request that's outside of the bridge's window, it's never going to see it, because the bridge will never have claimed it from the parent. So the windows claim a region of the address space on the top side, and we subdivide that to hand out things to the children. And some bridges might have to kind of deal with translating the addresses as they go across the bridge. In particular, you heard me mention, I didn't mention it too much earlier, but PCI has this notion of I/O ports, because it's something that x86 has in their CPU architecture. But a lot of other CPU architectures don't have dedicated instructions to access this alternate I/O address space. And so what they do is they take some region of their memory address space, and they reserve that to kind of be a window for I/O ports. And so when you read or write to an address in one of and kind of this specially mapped window, the bridge translates that into a request not for a memory access, but a request for an I/O port access. And so sometimes bridges will do things like that. So let's walk through an example kind of similar to what we talked about before, but this time we're going to kind of think about it as a bridge. So I'm just listing the kind of that little MMIO region we had before in the 3.5 gig to 4 gig range. But this time, instead of having only devices that directly access that, I've still got the GPU, because it's kind of directly attached to PCI bus 0 in this case. But now we have a couple of bridges. And each bridge allocates a chunk of that memory address space for the devices living behind it. And then I might have a bridge that has nothing behind it. So it's reserved the address space, and it'll listen for requests and send them off into the void where they don't get responded to, or they get responded to with a default, which says nobody cared, nobody listened. Or I might have a bridge with one device, or I might have a bridge with a couple of devices behind it, so that you can have multiple things kind of listening behind the bridge. So that's what the hardware is kind of doing. And so now I'm going to transition to talk about how, and our software device drivers, in particular our software device drivers that are kind of handling buses, how do we deal with that? How do we ensure that the NIC gets a resource that it can use, for example, that is going to get one that we listen to? So in FreeBSD, we have a tree of device objects that we create in a hierarchy. And anything in that tree that has other children is a bus device. So if it is a tree, then basically you have leaf devices and you have interior nodes, and all the interior nodes are bus devices in terms of how FreeBSD talks about them. And that can include things that are physical buses, like a PCI bus. We actually instantiate a logical device or device T object for a given PCI bus, and other buses like ISA. But bridges are also a kind of bus device, because that's how we represent them. And this is also true in OS 10 actually as well. So we have a separate device abstraction to represent a PCI bridge that talks either between two PCI buses or from the system bus to PCI. And so I should back up a little bit. As I mentioned, a bridge is going to have a parent that's a bus, and it's going to have a child that's some kind of bus. And then we have another set of buses that are these kind of, you might call them pseudo buses. They're not correlated with some physical bit of wiring on the box, but it's some way that we can collect multiple logical devices together. So an example of that is we have a top-level bus device called Nexus 0 that's a platform-specific driver. That's the anchor for all the device tree we build for the rest of the system. So we can have several children, but it's not a physical thing. It's just where we start hanging off the top nodes of the rest of our system. And also, for example, ACPI. There is no physical ACPI wires in your system. It's just a way that the firmware can communicate a kind of hierarchy of namespace of its own notion of devices. And we start with the top level of those and kind of attach those to a logical ACPI bus. And the same with Simple Bus, which is used for device tree like FTT and so forth that was used in platforms like ARM. So here's a picture of a non-exhaustive and simplified notion of what you might see inside a FreeBSD system. So at the top, we've got a Nexus bus device. In this case, it's got an ACPI child. The ACPI child has, in this case, at least one child device for a host to PCI bridge. So kind of the anchor of the top of a PCI Express hierarchy. Then we have a logical device that represents the PCI bus below that, that's, like in this case, PCI bus 0. And then we have a couple of PCI devices that are attached on PCI bus 0. So we have the GPU and a couple of PCI to PCI bridges. And I have an error. So there should be a little PCI bus here and here, and my slide would be even harder to read. So I guess ignore this part because I got it wrong. But in particular, notice how there's a bridge, then a bus, then a bridge when we're going across this. If you were to draw this in some other ways, you might only have kind of this. You might not have the bridge, or you might have just the bus. For example, in the ACPI namespace, they don't split these up into two things. And these actually, if you were to look on FreeBSD, both of these would have the same ACPI logical handle associated with them. But we choose to split them up for various reasons and it makes some of the resource management simpler. All right, so apologies that I messed up and didn't. I did this graphic today, and so. All right. So those are bus drivers, things like buses and bridges. Now how are we going to manage the resources that we talked about, like memory mapped I/O in particular, inside of these bus drivers? So we need these drivers to provide access to these shared resources to children. So children devices, a device driver pops up and it wants to map its bar so it can read, write some registers. It's going to ask the bus to kind of do that on its behalf. So they're responsible for figuring out how to allocate a resource, if it's fixed or not, or if it's a variable that can be moved around and they need to find the right space to move it around into. They're responsible for all of that. One of the things that a bus driver is responsible for doing is it needs to ensure that when it gives you a resource, it doesn't conflict with somebody else's resource that's already handed out. These systems don't work well with ambiguity. You can't have two devices listening to the same address. It's going to be undefined who wins, or if somebody wins, or nobody wins, or you get a machine check, or something else. So it's up to collectively the bus drivers in the system to avoid conflicts and avoid giving out the same address to multiple things. They also, to function correctly, a bus driver needs to give valid resources. They need to give, for example, when I had the example of the PCI bridge and the NIC was behind the bridge, it needs to get a resource that's in that bridge's window so that if you're trying to access the NIC, the access is going to work and make it all the way down. If the bridge were to hand out an access that's outside of its window, then that resource will never work. So the bridge has to be responsible to hand out valid resources. I mentioned interrupts earlier. We have to hand out what the interrupt resource the device asks for that represents the interrupt it's actually wired to. And that's how we ensure that you can attach your interrupt handler in the right place so that when your device interrupts, your handler is the one that gets executed and not somebody else's handler or no handler. And then once we've actually allocated these resources that are valid, we actually have to let you use them. So if you're doing memory mapped I/O, you need some way to actually map the memory mapped I/O and some way to actually access the registers. And for interrupts, you need to be able to actually add and remove interrupt handlers. So given that these are our responsibilities, now I want to talk about a couple of the abstractions that we have in the kernel for how we deal with these. And the first one is something called a resource manager, which is struct rman in this tree. And rman's role is to describe some kind of address space. You can think of it some kind of thing that has addressable chunks that you can have a bigger, wider address space that you can chop up into smaller regions. So effectively, you can think of it as a special purpose address space manager. We have FreeBSD now, we have several address space managers. We have things like vmem that back kmem for KVA allocation. When NuBus was first written, we had the specific one for kernel memory, but we didn't have others, and so this rman was special purpose written. And it has some quirks specific, like it'll save references to the devices that allocate resources. So I don't think we could quite replace it with vmem today, but if you were to start writing this today, maybe you would pick an existing allocator like vmem to do this. But this is what we have. So it's special purpose for device resources. And rman can describe a real address space, like CPU physical memory, but it can also describe kind of a virtual address space. So when, for example, for interrupts, we will take the set of interrupt controllers in your system and logically assign kind of ranges of interrupt numbers, or what we call RQs, effectively little cookie values, to all the pins and kind of name them by number of the pins and all the interrupt controllers in your system, and use those kind of names for how we actually, the values of the IRQ resources that we hand out. And so we kind of create a virtual address space out of all these pin numbers for what constitute IRQ resources. The way an rman works is you initialize a resource manager with kind of the absolute max and min of whatever address space you're working with, and then you add one or more regions, which can be a subset of the absolute top and bottom of your address space, but a set of active regions that are available inside the rman. And when you go to allocate resources, it's only going to hand out something that's in one of the regions. So you can have a sparse address space. You can have an address space that says, logically, I can go from 0 to 264, like my earlier picture of the x86 memory address space, but I know that only certain parts of it are actually something you can allocate from. And you'll see maybe some examples of when that's useful later. And then when you're working with rman, if you allocate a resource, we return that resource in an instance of a struct resource object for a single contiguous region of space that we've allocated. And that's what device drivers end up using as their handle for resources. And one of the things rman does is it takes care of avoiding resource conflicts. So if you try to allocate something from rman, it will fail if you do a request that it can't satisfy because it overlaps with things that are already allocated, or it will ensure that if you give it a sufficient wildcard request of a given size, it will go find a free region for you. So rman takes care of the part of the problem of avoiding resource conflicts. So our bus device drivers can rely on rman to do that. They don't have to solve that problem themselves. So I want to shift next to talk about kind of how do we name or talk about device resources for given devices. So in FreeBSD, the way we choose to name devices is by a tuple of a type and a resource ID, which commonly the variables we use all over the kernel are spelled RID, so I might call it RID. Types include things like sysres memory, which is your physical memory address space, or sysres IRQ for interrupts. We also have a couple of other ones I'm not going to mention, but another type of address space that may not be an obvious one at first to think about are PCI bus numbers. So a PCI Domain has bus numbers from 0 to 255, and bridges can claim a region of those, kind of like an I/O window. And so we actually have rmans to manage those bus numbers, and that's how we manage avoiding conflicts and all the same problems with bus numbers. And then a given bus defines what kind of scheme it's going to use for resource IDs. So some buses, like ACPI and Simple Bus, where they can just enumerate when you ask it what resources the device has, they use a pretty simple scheme of just 0 to n for however many resources you have. For example, in ACPI, when we enumerate a child, we get to call a method underscore CRS to get the current resources for a child device. And then we can walk that list, and for every memory device we see, we'll start with the first one being 0, and the next memory device being 1, and so forth. And the first interrupt, and probably only interrupt, being 0. And if there's an I/O port resource, the first one's 0, the second one's 1, and that's kind of how they're all named. In PCI, we do something a little different. In PCI, we use the offset of a bar in the PCI config space address, or well, PCI config space, as its kind of resource ID. So if you have the very first bar, bar 0, we will use the address of bar 0 in PCI config space as its resource ID, which happens to be hex 10, and so forth for all the different bars you might have. In this case, this means that we don't have, in other buses like ACPI, you might have 2 different resources with a resource ID of 0, one a memory resource and one an I/O port resource. But in PCI, you don't have that, because in PCI, a given bar is one or the other. And so, PCI bar 0 is either going to be a memory or an I/O port resource. Or if the bar is not valid, there won't be a resource for that at all. And then for interrupts on PCI, we use 0 for the kind of legacy interrupt pin interrupt that you can have. And for message signal interrupts, we use 1 to however many you've allocated. And that's how you can tell which type of interrupt you're working with on PCI. But the important part, I guess, is the RID is something the bus defines. And so you have to know when you're writing a device driver what your bus uses. And as a bus, you have to pick a scheme for how you're going to consistently name your resources. So how do we keep track of that model? We're going to have resources named by type and RID and as a tuple, and we're going to keep track of what resources our devices have. So to help with that, we have a data structure called a resource list, which is struct resource underscore list. And it holds a linked list of entries that are of type struct resource list entry, somewhat obvious. And each entry holds, which we often in the source code will call the variables RLE. So each RLE holds things like the type and the size of the given resource. It also holds its RID and kind of the valid range. In some cases, the valid range might be very constrained. If it's a firmware assigned range of exactly where the resource lives, then the start and end of the range correspond to the size. But if it's actually variable and you could move it around, then the start and end might be much broader, and the size tells you, within this range, I need you to find a chunk of this size to use as the resource. The mere existence of an entry in this list does not mean that the system has gone and allocated a resource for you. Resource lists are just how we keep track of what the set of resources a device kind of can use and has available, but not necessarily that they're allocated yet. When we do want a resource, then we'll take the information in a resource list entry and use that to call a resource manager to say, give me a chunk of resource of the right type. And then when we get back the resource object for that, that becomes kind of the backing resource for this RLE, and we'll save it in the RLE. So let's talk a bit, I know I'm just throwing a fire hose of stuff at you, about a bit kind of this life cycle or states that an individual device resource can go through. So when we've added a resource, we've put it in the resource list entry, and I didn't really quite name that. But one of the things we can do is some buses don't know about the resources a device has. Like the legacy ISA bus, we rely on obscure things like hints, or there might be some other devices that kind of use other tables to find what resources they have and have to manually add them. But on many buses, like PCI or ACPI or other things, the bus itself has a way to find out what resources you have been assigned. And if that's true, then that bus needs to ensure that even if you don't have a device driver attached, that resource is still active, and we need to make sure it's reserved from the address from kind of the resource manager, so we don't hand it out to somebody else that does a wildcard request and says, I just want a random chunk of address space of size X. So buses that can identify the resources of children belonging to them while they're enumerating them, they're responsible to reserve the resource even if the device driver is not attached yet to ensure that nobody else can get it because it's actually active even though the device driver is not active. But once the device driver actually asks for the resource by calling bus alloc resource, then the resource is allocated. And that means that we've allocated something from the resource manager and we definitely know the child has it. But in order to actually use a resource, an allocated resource needs to be activated. And normally what that happens is when you call bus alloc resource, you can include a flag, RF active, that almost every driver does, which kind of does this all in one step. And I'll talk more about why where active can, I guess I'll do it now. So one example of why active can be separate from just having the resource allocated is active might mean, for example, you've turned on decoding for the device. So in PCI, for example, we have a command register that decides whether or not your PCI device is actually listening for requests for memory access or IO port access. And so one of the differences of an activated resource versus an allocated resource is an allocated resource may not actually have decoding turned on. It might have already been by the firmware, but it's not guaranteed. Whereas when you activate the resource, the PCI bus is going to make sure that decoding is turned on by writing the right bit to the PCI command register for your device. And then if you have an activated resource, that means it's all hooked up in the system and decoding, that's great, but you as a device driver might still actually need to use it. Like you might need to read and write a register. And for memory and IO port resources, that's yet another step. You need to map the resource to have some kind of mapping you can use. And typically that's also implied by RF active. There are some ways to turn that off and to maybe request a specific mapping, but we won't go into more of that right now. Whoa, that's not what I wanted. All right. So we talked a bit about resource lists and what we store in them. What are some of the actual functions that a bus driver uses out of this API? So first of all, bus drivers have the ability to store data about each child device. If you're familiar with device drivers in FreeBSD, you know that devices can have a soft C. There's software context that a device driver uses to store information about itself associated with each device. So if I'm a device driver for a NIC and I want to have somewhere where I store my MAC address, I'm going to have a soft C that can have multiple for each instance of the device that's in the system, and I'm going to store the MAC address there. Well, instance variables, or IVARs, are kind of a similar thing, but it's not for the child device driver, it's for the parent. It's where the parent bus device gets to store information about each child device. And this data structure is the right place for a bus driver to put its resource list. So if you're going to be tracking resources, one of the things the bus driver needs to do is it needs to instantiate a struct resource list inside the IVARs for each of the children, so in each IVAR for each child. And you can use resource list init to create those, and you can use resource list free when you're deleting a child to clean up and kind of free any entries that are left hanging around. As you're enumerating resources, as a bus driver, for example, PCI, if you're walking all the bars and sizing them and figuring out how big they are, you can use resource list add to add entries to the list. And if you need to reserve them, like I mentioned PCI can do, there's resource list reserve for that. And then finally, there's a couple of helpers, resource list alloc and resource list release, that are useful in your bus driver's bus generic or bus alloc resource and bus release resource methods. So they're helpers that take care of finding the resource list entry, making sure that the device has asked for a resource that's a known one, and then asking the parent for the resource and kind of fixing up the RLE after it comes back down, and then unwinding that and release. So the last really big topic I wanted to talk about, yeah, we might make it on time, one of the things we have is we have a couple of different sets of generic helper routines for bus drivers to use so that you don't have to re-implement everything every time in a bus driver. We can share and avoid some of the copy and pasted code, at least some. And we have a couple of different groups of these. So the first one, and I'm going to talk about all three of them, is named bus generic and then the name of the method. There's a bus generic RL, and then the name of the method, and then one that I added this past year is bus generic rman, and then the name of the method. But we're going to walk through each one of these individually. So the first one is just bus generic star, and for the most part, these methods are quite simple in that they assume that I as a bus don't actually handle this request, but my parent will handle it. And so for the most part, the bus generic methods, like bus generic setup interrupt handler or something like that, they just turn around and hand the request up to the parent and say, here, you deal with this. Like, I don't actually deal with this directly, but you can deal with it. And so using this, request will kind of bubble up through the device tree until they get to a level of some bus driver that does handle it. Then the request is handled and it kind of, the reply falls back down. But, this is one of my soapbox parts, there are a few cases in this API that I think are wrong. But I don't think they're actually good methods, good matches for being a placeholder method. So the first one is something called bus generic probe. And bus generic probe's job is it is actually a way to allow device drivers for a given bus device to run their own kind of special routine called an identify routine to try to discover devices that the bus device might not know about. That's kind of obscure. It's used more on pseudo buses than on physical buses, but it's a way that a driver can kind of create devices when it needs to that are attached to something else. But the key thing about bus generic probe is that that has nothing at all to do with a device probe routine. A device probe routine's job is to decide if a candidate device is a device that it as a driver can handle. And if it is, it's supposed to set the description of the device and return a value saying kind of how well it can handle it, like what its preference. Is it a very specific probe device or not? And bus generic probe doesn't do any of that at all. So it's horribly named. And nothing should use it as a device method for device probe. And I think it should be named bus identified children, meaning go walk all your device drivers and try to identify any children using the device driver to do that. In fact, one of the things I've been doing this week is that the next few slides, I've been hacking on all this, and I've got a queue of about 40 patches now because I found a bunch of other device driver bugs doing it. The next one that I think is poorly named is called bus generic attach. So bus generic attach is what it does currently is it assumes that your device bus, your bus device already has children devices, and then it will try to probe and attach all the children devices you already have. The only problem is, where did the children devices come from? They have to come from somewhere. And what's supposed to happen is your bus should have an attach routine that first goes and figures out what kind of child devices you have. Maybe it calls bus identified children to let device drivers find it, or maybe it does a scan of your PCI bus. It needs to do something to add the devices. Then it can call this routine to actually go attach drivers to the devices. But standalone, it's not good enough. If you just make this your attach routine, it's going to do nothing because there's no child devices to attach. Like you have to create them and attach them. So similarly, I think it's not actually good as it's named and should be renamed to bus attached children to just indicate the part of kind of the logical step it's doing. And then lastly, we have bus generic detach. And this one is a little more, this one's almost to what it should be. But in particular, in general, detach routines for a device driver are supposed to unwind all the state that is done in an attach routine for the device driver. So if you've allocated resources, you're supposed to free the resources. If you've set up an interrupt handler, you're supposed to tear down the interrupt handler. So if you've added children devices as part of your attach routine, you should not only detach, but you should delete the children devices as part of your detach routine. And today, all bus generic detach does is it goes and detaches drivers from all your children devices, but it leaves them hanging around. So you have all these kind of orphan children devices left around. So, to my view, it's not sufficient to be a detach routine standalone as it is, because you need to do both things. You need to detach drivers and you need to delete the children. So I think it should be renamed to just bus detach children. And we already have an existing function called device delete children, which I argue should maybe have a bus prefix after doing all this. And its job, it will actually do the deleting of everything. So what I've actually gotten to is in my tree now, bus detach children actually does both steps. So first it goes through and detaches everything, and if that all works and none of the child devices rejected the attempt to attach, then it goes through and deletes everything, so everything is fully cleaned up by the time it returns. So that's the end of my soapbox segment about bus generic. So the next set are something called bus generic RL. And this set of routines, it's not near as many as kind of bus generic star. It's a subset of bus routines that work with resource lists. They assume that your bus driver chooses to use a resource list to name all the devices for your children's devices. And in that case, it gives you a couple of helper routines that you can just use in your dev methods without having to implement all the logic yourself. In particular, if you allow child drivers to add their own resources using bus set resource and bus delete resource and to query them with bus get resource, you can use generic versions of these and it'll handle all that logic. It also provides methods for dealing with bus alloc resource and bus release resource. And in particular, these call, under the hood, they call resource list alloc and resource list release for you. And that's all great as long as you're just naming resources and allowing your parent device to kind of handle the allocation of them. And that's true for things like the PCI bus driver, for the most part. The one caveat of using these helpers is your bus must implement a new method called bus get resource list. And the job of that method is, given a child device, what is you're supposed to return a pointer to the resource list for it. So typically what you do in that method is you get the IVARs for your child device, and you return the resource list that you stored in the IVARs, because that's what you're supposed to do if you're using resource list. So the last set of generic bus methods, how am I on time? Well, I'm not terrible, are called bus generic rman. And these are ones that I wrote this year. Well, I wrote them several years ago, but I finally got them merged to the tree this year, is a more accurate way of saying it. That tries to reduce a bunch of code duplication we had, in particular in many of our Nexus drivers, but also in a couple other places. And the idea of these helper methods is you're not just tracking resources for children that you're naming in a resource list, but you actually have a resource manager. You're responsible for some kind of address space, and you're responsible for actually sub-allocating things out of that address space to satisfy requests. So for example, the Nexus devices that sit at the top of our tree, they're responsible for the global address spaces we have, like the set of all the interrupt lines, or the set of the entire CPU physical memory address space. So they need to work with an rman to sub-allocate and figure out a suitable resource allocation for some child device that wants a resource and then hand it back down. And so these are a set of helper routines for several bus methods that will do kind of all that for you. The one caveat is you need to implement a new device method called bus get rman that, given a resource type and flags, will return what rman is suitable for your bus that your bus device has for that given type of resource. It also has a couple of other helpers that it'll handle bus activate and deactivate resource for activating and deactivating resources. The only trick here is a couple of years ago, I added new methods called bus map resource and bus unmap to solve a couple of problems. One of them was kind of actually this problem, is I wanted to be able to have only the logic that's actually specific to, say, x86 or ARM64, which is how you map a resource. I wanted to have a hook that's just that. And also so you can map only a subset of a resource and not the whole thing, because there are cases when you'll see where you need to do that. So you have to implement those two methods. And if you do that, you can use all these kind of generic helpers, and it took out a lot of duplicated code among many of our Nexus drivers. So that's kind of the overview I wanted to give of some of the APIs we use. And for whatever remaining time we have 5 minutes, we'll see how this goes. I wanted to walk through a couple of bus drivers we have in the tree and how we kind of put these bits together to implement these drivers. So the first one I want to talk about is the driver for PCI bus themselves. This is, or the PCI bus. Note that this is the buses that have a bridge at the top, either a host to PCI bridge or a PCI to PCI bridge, and then various PCI devices into the bottom, which can be more PCI to PCI bridges, or they can be a NIC or a USB controller or something like that. But the logical bus that has a bridge at the top and things at the bottom. So PCI X devices represent those. PCI buses don't inherently have any kind of address spaces that they're responsible for. That all comes from the parent bridge. It's the parent bridge's job to actually deal with finding me a resource when I need it. But they are responsible for keeping track of what resources a given PCI device has. So they do use resource lists. And there is a caveat about resource managers. There's this weird thing that VFs have to do for SRIOV that I'm just going to ignore for this talk. But for the most part, if us ignoring VS, they don't have to deal with resource managers. They're just dealing with keeping track of what resources I have from my bars. So as we enumerate devices, we size all the bars. We use resource list add to add every bar to the resource list for my given device. If the device has actually been assigned a valid range by the firmware during boot, then we'll also reserve that resource range to ensure it's reserved. And then that means that for the most part, we can just use bus generic resource or RL and resource list star to handle a lot of the resource management. And we don't have to deal with too much of the gross details in the PCI bus itself. And then, as I mentioned earlier, the PCI bus does have custom methods for activate and deactivate to deal with the bits in the PCI command register so that we turn them on when you're activating a resource. So the next one I wanted to talk about is the PCI to PCI bridge driver, which I have a bit of a love-hate relationship with. So we mentioned earlier, in the earlier part of the talk, about the fact that bridges need to have I/O windows, and they need to reserve space for the I/O windows from the parent, and then suballocate that to children. So in our current driver in the tree, we actually create new resource managers for each I/O window. And we allocate a resource from the parent bus for my entire window, and then we add those, whatever that resource that we got from the parent, we add that as regions to the resource manager for the corresponding resource manager, and then we suballocate out from that to hand out resources to our children. And the resource that we get from our parent, we don't actually need to work with it and do individual register reads and writes. So we mark it as active, but we say we don't need a mapping because we don't need to create arbitrary mappings we're not going to bother using. However, the one tricky part of this is when a child device wants to allocate a resource. It gets some resource from my rman, and that's a smaller resource than my window. It's some subset. And I now want to give a valid mapping to my child device driver so it can do memory mapped I/O. It can read and write the registers. Well, how should I do that? What we used to do when I first added resource managers to the PCI driver was a gross layering violation where I would take that resource that had been allocated down below and I would pass it all the way up to the root of the tree to construct a mapping. And that worked. If you ignore things like translating bridges, it worked. But it's kind of gross. Really, bus driver, you should only have to be responsible for and dealing with the resources that you've handed out to somebody. If you didn't, if you're a bus driver and you get a request for a resource, you should handle it. It shouldn't be your job that you ask somebody else to handle something you created and handed out. And so the way I resolve that is I have this parent resource that I've got from the top side. And when I want to map some small part of it, then I explicitly in this driver ask for a mapping of just that small part of it. And I get the mapping back up from my parent, and I turn around and install that mapping in the resource that I hand to my child, and then it gets a valid mapping for just the part that it cares about. But I've allowed the parent to figure out how it wants to do the mapping. And if it needs to do translation or whatever, I allow that request tailored to kind of go up the tree. So what does that look like? So let's go back to a little bit of our hardware example from before. So we have physical memory. When the PCI to PCI bridge driver attaches, where am I at? 1 minute? All right, I'll try to finish this. When the PCI to PCI bridge driver attaches, it gets its window resource kind of for the whole I/O window out of RAM, and it creates a resource manager that's the whole thing. Then when my NIC driver attaches, it's going to ask for its first bar. So first we go to the resource manager and say, hey, can you give me the resource for bar 0? And it does that. The next step is we need to get the mapping. So for the mapping, I went backwards. For the mapping, we go find just a little subset of this giant resource we got from our parent, and we say, give me a mapping for that. Then we copy that into the bar resource and hand it back to the NIC. And now it has a fully constructed valid resource with a mapping for the thing that it allocated. And so we'll keep doing that for another bar in the NIC or maybe a USB controller. And that's kind of the final state that we ended up with and how we get valid mappings. All right, I think I'm done on time, so I can't do my last 2 examples, but you can come ask me at the end. So that's it.
Can you give us another example?
I have 2 more on my slides. But.
Thank you, John.
Sure.
I think we can entertain 1 or 2 questions if anybody has any.
Yeah, here. Okay, and you should read that and you can ask questions. because these are useful tools.
Looks like no questions from the audience. In that case, please give John a good hand.